So today, the title of my talk is a learning approach to the optimization of massive MIMO systems. So this is joint work with my postdoc, Fuad Shirabi, and PhD student Karim Atia at the University of Toronto. So this talk is about the design of massive MIMO systems. And massive MIMO is a key technology for future 5G or 6G systems for enhanced mobile broadband. So specifically, I want to talk about the optimization problem concerning massive MIMOs. And if you look at how conventional communication systems are designed, they're always designed in a two-step process. Typically, we send some pilot signal to estimate the channel. Then once the channel is estimated, we optimize the system based on the estimated channel. Now, for massive MIMO systems, channel estimation can be challenging because we have large number of antennas. We're talking about 64 or 256, a large number of antenna array, large antenna array. So the channel estimation problem can be challenging. And further, even after the channel is estimated, the optimization problem involving this large antenna array is also non-trivial. So in this talk, I'm going to examine the role of machine learning for performing this optimization process. And the idea of this talk is as follows. It is possible to engage in a data-driven approach for such an optimization problem. And we can do that while bypassing explicit channel estimation. And I'm going to talk about how to do this and the advantage of bypassing channel estimation. So let me talk about machine learning versus mathematical programming. Traditional communication system design is always done using mathematical optimization techniques. And this is an appropriate approach when we have a highly structured model over well-defined problems. And defining the solution of the problem often rely on having an often convex optimization landscape. So here's an example. If you have a model system, what model defines an optimization landscape. And the parameter here, so the parameter space, the x and y axis is a parameter space, then you have an objective function as the sort of z-axis. So the optimization process is that of finding for which parameter is the solution, is the objective optimized. And that where the objective function is optimized, this is the solution. Okay, so this is a traditional approach of first defining the model, then to optimize. But in this talk, I'm going to look at an alternative approach. Okay, so instead of defining the model first, then finding the solution, I'm going to use a neural network to map directly from the model parameters to the solutions. So what I'm advocating is the following scenario. If you think of what mathematical algorithm is, optimization algorithm is, an algorithm is basically that of taking a problem instance, taking the parameter of the problem, for example, a linear programming problem, you give me the description of the problem, and when I output the optimized solution. Okay, so this is what classical mathematical optimization algorithm is. So instead of performing the classical mathematical optimization, what we can do instead is to train a neural network to mimic the mapping from the problem instance to the optimized solution. Okay, so if you want to do this in a supervised fashion, that means you solve many different instances of the problem. Then I'm going to train the neural network such that the output always match the optimized solution. So this is the training process, and in the testing stage, I'm just going to deploy this neural network. So then when a new problem comes along, I can output the desired solutions. Okay, so this is the approach that we're going to take in this talk. So the traditional approach for communication engineering is to first model and to optimize, but machine learning allows us now to be data-driven and thereby skipping the modeling altogether. And this is made possible because this neural network, if you have enough parameters in the neural network, this neural network can mimic any functional map from any input space from any output to any output space. So this allows us to incorporate a vast amount of data over potentially poorly defined problems. And this is now computationally feasible because nowadays we have highly parallel implementation structure for both the training and the testing of the neural networks. So here's how I see the role of machine learning for communication system design. You see, communication engineers traditionally have invested heavily on channel models. However, models are always only an approximation of the reality. And further, model parameters need to be estimated, and this estimation process always have inherent estimation error. So what we're going to do in this talk is to advocate an approach of using machine learning to skip the channel modeling stage and to proceed with an end-to-end communication system design. The advantage of the system is that we can do direct system optimization without the intermediate stage of channel estimation. And this allows us to implicitly account for channel estimation error and even allows us to incorporate additional sign information. For example, the location of the UEs, location of the users can be used as sign information in the optimization process, and that can be incorporated in a neural network architecture. And the overall advantage of this approach is it allows us to reduce the required pilot length. So in this talk, I'm going to address some of the challenges of using machine learning technique to pursue this program. And I'm going to look at the generalizability of the proposed approach to different system parameters, and look at the interpretability of the plane solutions. And for any of these approaches to work, we need a large amount of training data. Okay. All right, so in this talk, I'm going to provide two examples in massive MIMO system design for millimeter wave communications, where this approach is shown to have a very good performance. In the first part of this talk, I'm going to look at the channel sensing and hybrid precoding problem for the time division duplex massive MIMO systems, TDD systems. And in the second part of this talk, I'm going to look at the frequency division duplex massive MIMO systems. And there I'm going to look at multi-user channel estimation and feedback problem. Okay, so this talk will be divided into two parts. Okay, so let me talk about TDD versus FTD systems. So recall that for massive MIMO system, how to obtain channel state information is always a key problem. So there are really two different channel system architectures for to obtaining channel state information. One is use a TDD system. Here we assume that the uplink and downlink transmissions are interleaved in time, and we further assume that the channels are reciprocals of each other. Okay, so in other words, the uplink and downlink are within the same coherence time. So then in this case, the channel estimation can happen in the uplink. So the users transmit pilots, and those pilots are received at the base station. And then based on the received pilots, the base station will estimate the uplink channel. But then we assume that downlink channel is the reciprocal of the uplink channel. So then the base station will collect the channel from all the users, then proceed with the precoding step of designing the precoder for the downlink transmission. Okay, so this is how TDD system work. But there are also massive MIMO systems where uplink and downlink are implemented in the FTD fashion, in different frequencies. In those cases, then the channel reciprocity no longer necessarily hold in different frequencies. In this case, then what we need to do is to do channel estimation in the downlink. So the base station will transmit a downlink pilot, and that's received by the user equipment, and the users will estimate their own channel. But then once the channels are estimated, it needs to be fed back to the base station. Okay, so the base station need to collect the channels from all the users, then proceed with precoding. Okay, so FTD systems is more challenging to design than the TDD system. So in the second part of the talk, I'm going to talk about FTD systems. Okay, so let's move to the first part of the talk. Let's focus on TDD massive MIMO systems. And the main task is to perform channel sensing and to proceed with precoding. Okay, so here is a more detailed schematic of the massive MIMO system considered in this talk. So in this work, we consider the precoding design at a millimeter wave frequency. And the traditional MIMO design always have a dedicated RF chain per antenna for every antenna. However, when you have a massive MIMO system with lots of antennas, equipping an RF chain for each antenna becomes expensive, and its power expenditure-wise prohibitive. So what's commonly done is this hybrid architecture, where we have the number of RF chains equal to the number of users. And those RF chains then drive multiple antennas. Okay, so for example, you have 10 users, you have 10 RF chains, but you could have 64 antennas. So in effect, the precoding at the base station is divided into two parts. One is the digital precoding part, and the other is the analog precoding part. And this architecture is called hybrid precoding. So the downlink precoding design problem is that of designing both the digital precoder as well as the analog precoder to attain to maximize some kind of system performance. Okay, so that's called the digital precoder VD and the analog precoder VRF. Okay, so this is the parameters that we want to optimize. So let me set up the problem. Okay, so we are in the TDD operation. This means that the base station does not know the CSI initially and has to learn CSI based on the pilot training in the uplink. All right, so we assume channel reciprocity, and base station acquires CSI through uplink training. And in the uplink pilot phase, what you transmit is every user will transmit orthogonal pilots, and this pilots is X here. Then, because we have only have limited our number of RF chains, so we need to set this analog precoder in the uplink as some precoding matrix. And this precoding matrix is called WRF. So this is what we call a sensing matrix. Then the received signal is denoted as RL. So we transmit L pilots. L go from 1 to capital L. So we repeat this over L time frames. Okay. So at the receiver, you receive the base station receive this RL signal. Then it will match with the orthogonal pilots. And this is essentially received pilot at the base station. So the downlink precoding problem, at a high level, can be thought of that of mapping the received pilots, Y1 to YL, to the analog precoder and the digital precoder. Okay, so this is the mapping that we will try to learn. So we can formulate the problem as follows. We want to maximize some kind of system objective. The system objectives, for example, can be the sum rate across all the users. And the rate is log of 1 plus the signal to noise ratio, noise and interference ratio. And this maximization is over two sets of parameters. One is this mapping. How do we map the received pilots to the precoders? So we want to optimize this mapping. And second thing is we want to also optimize the sensing matrix. This uplink, we have a freedom of designing the sensing matrix. So we're maximizing over these two set of parameters. And we have the constraint that the sensing matrix, as well as this VRF, the analog precoding matrix, these are just phase shifts. So they are e to the j thetas. Okay, so this is our overall optimization problem. Okay, so let's see how do we solve this problem. And the traditional way of solving this problem is to divide this precoding step into two steps. So what we do is first we look at the received pilots. We first try to estimate the channel. This is H hat. This is estimated channel. And once this channel is estimated, then we come up with the analog precoder and the digital precoder. Okay, so this is a traditional approach of channel estimation followed by precoding. What we're going to do in this talk is I'm going to advocate a direct approach. We're going to skip this channel estimation directly, and directly map the received pilots to the designed precoder that we're going to design. And the main advantage of this combined approach is that if we do this two-step approach, we necessarily have to define some kind of a distance metric to say how good our channel estimation is. Right, channel estimation is typically done with respect to some kind of minimum mean square error criteria. But these kind of minimum mean square error criteria does not necessarily directly correspond to the ultimate system performance of interest. So by combining these two, we no longer have to define this distance metric. Rather, we can just go directly for optimizing the system output, maximizing system output. And this is advantageous, especially when you have short pilots and when you have a significant amount of channel uncertainty. Okay, so this is what we're going to do. Sorry. So what we're going to do is we're going to formulate this optimization problem of maximizing the sum rate. And what we're going to do is replace this optimization process with a DNN, with a deep neural network. And this DNN will take the received pilots as the input and directly map the VRF and VD. Now, it turns out that this kind of DNN is difficult to train. The reason that this is difficult to train is because this VRF and VD enters multiplicatively in this system objective. And this kind of multiplicative relationship is difficult to handle for the deep neural network. And further, if we're just going to train this DNN as is, this lacks generalizability, because this DNN need to be designed for specific channel parameters, such as number of users. Okay, so if you design a DNN for 4 users, then if the system now operates with 10 users, you have to retrain the DNN. Okay, so that's not desirable. So what we're going to do is to propose an alternative architecture that's more generalizable and it's easier to train. Okay, so let me talk about my proposed design. The proposed design is as follows. What we're going to do is we're going to divide the pilot frame into 2 parts, the analog part and the digital part. And we're only going to use the DNN to design the analog precoder. And in the digital part, we're going to use a conventional channel estimation and precoding technique. Okay, so we're only going to use the DNN to design the analog part. And in designing the analog part, we ignore multi-user interference. And the reason we can do that is that we know that there's a subsequent digital part that will essentially reduce the interference, or you can even completely eliminate interference using zero forcing. Okay, so this is what we're going to do. So what we're going to do is to design the analog part using the DNN, while assuming that subsequent multi-user interference can be completely removed. And this allows us to define an objective function or a loss function for the analog precoding design. Without that, we don't know the digital precoding part yet, so it will be difficult to design the loss function. So in the analog design, what we're going to do is to maximize the system objective, and that objective is an approximation of the subsequent objective that we're going to get. All right, so this is the first step. And further, we're going to decompose the analog precoder design into K per user mapping from the received pilots. So this allows us to have a more generalizable architecture where we have a DNN associated with each user. And if the number of users changes over time, then we can just replicate this DNN multiple times. Then this allows us to have a generalizable architecture that's suitable for any number of users. Okay. So let me draw a picture to show you how things work. So here's how the training of the DNN work. So in the training, we can think of it as having the channels as input to the DNN. And the output is the VRF, the analog precoder, which is a function of the channel realizations. Okay. So the overall system has 2 components. One is the analog sensing part. So this is the sensing matrix I was talking about earlier. So based on these sensing matrix, we get the received pilots. Then those received pilots are fed into the deep neural network. And we're going to do this 1 user at a time. Okay, so each user takes the received pilots and map to its own analog precoder. Then we replicate this K times so that we can get K analog precoders. And what we're going to do is going to tie the weights of these neural networks together across these K users so that we only need to train a single user DNN and we replicate it K times in order to have the entire system working in a way that gives us the correct analog precoder. Okay, so as I mentioned before, the loss function is just the sum rate, assuming that the interference is not there, is absent. Okay, so this is the deep neural network architecture for the analog pre-design stage, analog precoding design. Then once the analog precoding is designed, then we proceed with the digital. Okay, so here is a deeper look at what each of this G and the analog precoding neural network look like. So we have an analog sensing stage. Then it's basically multiple fully connected layers. And the output of that is mapped to the face. So there's a phase mapping layer at the end. Okay. So what's interesting is that the analog sensing layer can be thought of as 1 layer of the overall deep neural network. But this layer has no non-linearity, so it's actually a linear layer, but you can still use backpropagation to train this. So in other words, we can train the analog sensing layer for free in the overall architecture. Okay, so this is the single user DNN. Then once the analog precoder is trained, then we proceed with digital precoder design. So there, things is easier because the analog precoder is already fixed. Then we can look at the equivalent digital channel. Then we estimate the equivalent digital channel, then subsequently use the estimated channel in the subsequent precoding design. For example, we can use zero forcing based on the estimated equivalent channel. Okay? But in the digital part, you still have to design the sensing matrix. And what we're going to do is we're going to use the analog precoder that's already designed as the sensing matrix in the digital training phase. Then with this as the sensing matrix, we can estimate the equivalent channel, and this equivalent channel is used for subsequent digital precoding design, for example, using zero forcing. Okay, so digital precoding design is conventional. The analog precoding design is based on the DNN. So here's how the overall architecture works. This is the analog training phase. This is the digital training phase. The analog training phase essentially takes the pilots mapped to the analog precoder. So this is the analog precoder. I'm going to use a downlink. But this analog precoder is also used as a sensing matrix in the digital training phase. Digital training phase also occurs in the uplink. So in this case, we just estimate the channel and use the LMSC to estimate the channel and using zero forcing as the precoder. Okay, so there are two phases here: analog and digital phase. In the analog phase, we decompose the DNN into the users, and we also tie the weights together so that the overall architecture is generalizable. And in the digital part, we set the sensing matrix as the VRF. Then we estimate the equivalent channel. Then we use convention design to design the precoder. Okay, so let me show you how well this works. Here's a channel model under test. So we assume a millimeter wave channel. We assume that there's an LP path, each with an angular arrival, and with an array response vector, linear array response vector. So this is the parameters of how many layers and how number of neurons per layer that we have implemented. Each layer has ReLU nonlinearity associated with it. And this is the main performance plot of the sum rate versus the amount of pilots. So remember, time frame L is the total amount of pilots. Recall that this total amount of pilots is divided into two parts, the analog part and the digital part. Okay, so we do a search to find what's the optimal partition of analog versus digital. So this red line is our performance of sum rate versus the pilot length. And the blue line is the perfect CSI case. So eventually, as the number of pilots gets larger, we can approach the perfect CSI case. The purple and the red line, the yellow curve is the baseline. So this yellow curve is to estimate the channel analytically using a compressive sensing method. Here's we used OMP. Then we use phase matching to design the analog part. And the purple curve is an alternative design where we use the DNN to estimate the channel under LMMSC criteria. Okay, so once the channel is estimated, then we design VRF and VD. Okay, you see that the main advantage of our proposed approach as compared to the separated channel estimation and precoding approach is that for the same performance, we can use much fewer number of pilots. Okay, so we save quite a bit of pilots. So this is our main performance simulation result. And the second the result I want to show is the generalizability with respect to K, with respect to number of users. So here, recall that what we're doing is we're replicating the same DNN across K users to have the overall architecture. So we don't need to train the DNN for, say, 4 users, then train it again for 10 users. We can just train one DNN and replicate it multiple times. You see that our advantage, this is our advantage. This is the average rate per user as a function number of users. So the average rate has gone down as number of users gets up, but the sum rate goes up. Okay, so you see that we maintain a consistent advantage as compared to the compressive sensing based channel estimation, and as compared to the channel estimation separated with precoding approach of the previous work. Okay, so this shows that our approach is generalizable. Okay, so let me summarize this part of the talk. In traditional model-based precoding design, channel estimation and precoding are always separated in order to make the problem tractable. But with the advent of data-driven technique, it is now possible to construct a hybrid precoding directly from the received pilots without explicit channel estimation. And that's the main point of this talk. And this paradigm allows end-to-end training of the overall system, including analog sensing. And the DNN can be designed on a per user basis in order to obtain a generalizable architecture. And we see that the resulting strategy can achieve outstanding performance. Okay, so this is the story of the TDD system. In the second part of the talk, I'm going to look at FTD Massive MIMO systems. Okay, so let me move on to the second part of the talk. So let's recall what FTD system is, right? In TDD, you do uplink training, then you do downlink beamforming. But in TDD system, because uplink and downlink are different frequency events, so you can no longer rely on uplink downlink reciprocity. So what you need to do is to do downlink training. Then the user will estimate the channel at the receiver at the UE side. Then it needs to feedback the user, feedback the channel to the base station. So what it means is that it needs to quantize the channel and feedback the channel to the base station under a limited rate feedback channel. Okay, and finally the base station does multi-user precoding in the base station based on the channel feedback from all the users. Right? So this is the overall architecture of the FTD system. So let me draw the FTD system in the following fashion. So you can think of the FTD system as a distributed source coding problem. So let me explain what that means. So what's really happening is each user is estimating the channel at its own distributed locations, right? So the channel estimation happens remotely at different users. And what the base station does, it collects the channel feedback from all the users, then arrive at a precoder. So this is really a distributed source coding problem because every user is estimating an independent channel. Every user's channels are independent. But what the base station does is base station is trying to compute a function of all these channels, right? So for example, if the base station wants to perform a zero forcing precoding, then it will take all these users together and compute this channel inversion, right? So this V is actually a function of all of these users' channels, right? So the traditional approach is the following. Traditional approach is that for every user, try to estimate the channel. They do a channel estimation process, then they quantize the estimated channel and send those quantized bits to the base station. Okay, so this is the base station side. And the base station then take these quantized channel, reconstruct each channel, then subsequently compute the precoder, compute either linear precoder or zero forcing precoder. Right. But the point of this talk, as you have already seen, is that this separated approach is not necessarily the best thing to do. The separated approach of first estimating the channel, then computing this functional channel is not necessarily the best because it's not necessarily true that minimizing, say, mean square error of the channel estimation will match with the ultimate system performance, right? So if we combine these two operations together and directly compute a function of these channels based on the quantized bits, that can potentially improve the performance. And further, I'm going to replace each of these channel estimation block and the reconstruction block and the precoding block by a deep neural network, and to do end-to-end training in order to maximize the overall performance. Okay, so this is what we're going to do for the FTD system. And this results in a much more efficient distributed feedback scheme in the overall system design. All right, so the point of the second part of the talk is to recognize that the end-to-end design of a downlink FTD precoding system can be regarded as a distributed source coding problem of computing a function. That function is downlink precoding matrix of the independent sources, and those sources are the channels under finite feedback rate constraints. Okay, so this the feedback link have finite constraint. All right, so this motivates us to propose a deep learning methodology to jointly design the deep neural network for channel estimation, as well as the deep neural network for computing precoder. In fact, we can think of the pilots as part of the neural network as a linear layer of the neural network, and we can even optimize over pilots. Okay, so let me show you how the system works. This is a system model. We have input in the training phase. We can think of channels as the input of the system. Then this feedback scheme of every user is that of taking received pilots and map that to the quantized bits that you want to send to the base station. And we do this for every user, and the base station collects the quantized bits for all the users and come up with a precoding scheme. All right. So the optimization parameters is that of figuring out what feedback scheme is the optimal for every user and what the precoding scheme is optimal. Okay, so what we're gonna do is to optimize over this feedback strategy and optimized over this beamforming strategy. So we can design this feedback scheme and the beamforming scheme, the precoding scheme together in order to maximize system performance. So the problem formulation is now maximize some kind of system objective. So here I take sum rays as objective. And the optimization parameters are the feedback strategy of every user and the beamforming strategy of every user. And we can throw in the optimization pilots for free. Okay, so we can optimize these three things all at the same time and do an end-to-end training. So this is like an autoencoder because there is rate limited feedback at the feedback stage. And what we're going to do is, replace this feedback scheme by a neural network, and also replace this precoder scheme by a neural network, and to do end-to-end training. So here, the downlink pilot transmission is just a linear layer. This uplink feedback strategy is a fully connected neural network, one for each user, with a nonlinearity after each layer. And the parameters of all these users are tied together so that the overall system is generalizable. Then this precoding scheme is also a multi-layer deep neural network. Okay, so then we're going to train for maximizing sum rate overall using backpropagation. So this is the proposed DNN architecture and how we propose to train this DNN architecture. Now, there's one problem with this, this training process. The problem is that these feedback bits are discrete. So this means that we need to approximate this digital output at the neural network with some kind of straight through approach or annealed sigmoid or adjusted straight through approach, you know, to have the gradients propagate through this digital approach. Okay, so we need to have this arctangent type of approximation in order to make sure that the gradient will propagate. All right, so let me talk about generalizability of this architecture. First of all, I want to make sure that this trained neural network can work under various different channel models to ensure robustness. So this is one thing we would do. And also we want to make sure that this overall architecture is generalizable for arbitrary k. K is number of users. So then what we do is we let all the users to adopt a common set of DNN parameters. And this common DNN, set of DNN, is replicated across all the users. And this is how this training is. This is how the overall system is generalizable, regardless of how many users are there. Okay, so this is how we ensure generalizability with respect to number of users. And also we want to be generalizable with respect to Q, with respect to number of feedback bits. So it turns out that instead of requiring the output of the neural network to have binary layers, we can make them to have analog output, then we quantize those analog output to different bits, and that turned out to work pretty well. Okay, so we can also ensure the generalizability with respect to B, the number of feedback bits. We design a common user-side DNN to operate over a wide range of feedback bits, and what we do is to have it to output soft information, then we quantize this soft information. So this. So let me show you how such a system works. So this again is a millimeter wave channel. So we have LP number path in the propagation environment. It's the same kind of millimeter wave channel that we used before, and this is neural network number of neurons per layer in the neural network. Okay, so this is a pretty large neural network for this problem. So this is a numerical result for comparing the performance of the proposed approach as compared to the traditional approach. So the difference between these two diagrams is one is for L equal to 8, L is the pilot length. This is for L equal to 64. So in this case, we are feedback limited. Here, both the pilots and the feedback is small. So the optimal performance limit is given by this blue curve. This is the perfect CSI curve with zero forcing. So here I'm also plotting the maximum ratio transmission curve with perfect CSI. This is the red curve, and our curve, the proposed strategy is this black curve. So this is plotting the sum rate as a function of the amount of feedback bits. Okay, so as number of feedback bits gets larger and larger, I'm approaching the perfect CSI case. So the key comparison point is this dashed curve. So these two dashed curves are zero forcing or maximum ratio transmission, but with a DNN designed for channel estimation. So here we first design a DNN to optimize the channel estimation process to minimize the mean square error. Then once the channels are estimated, we use either zero forcing or MRT. You see that these systems also improve as number of feedback bits gets larger. But the main advantage of our approach as compared to the channel estimation followed by precoding approach is that we save significant amount of feedback bits. Okay, so instead of 20 bits of feedback per coherence block, we only need something like 7 or 8 bits. Right? So this is the main performance comparison for the FTD system. And here are some plots of generalizability with respect to LP. LP is number of path, and with respect to B. So here I'm plotting the sum rate as a function of number of path. So the two curves of the proposed system is the black curve and black solid curve and the black dashed curve. So black dashed curve is the proposed DNN trained for every system, for every channel model separately. So this is a DNN trained for P equal to 2, LP equal to 2, L equal to 3, 4, 5, 6, etc. Okay, so this is the dashed curve. The solid curve is a DNN trained for LP equal to 2, but used in other channels. You see that when the LP is larger, we have a performance degradation, but still it performs better than the competing strategies. Okay? And again, the red and the blue curves are the full CSI curve. Right? So this shows that yes, we do have some performance degradation as the channel changes, as the channel model changes, but it holds up reasonably well. This last curve is the sum rate as a function of the feedback capacity B. So recall that we want to design a system that's generalizable with respect to the amount of feedback. So here we take S as the size of the DNN output. So here DNN output is a vector of size 8. So here we quantize into 1 bits versus 2 bits with 3 bits with 4 bits, etc. So 8 times 4 is 32. That's why we have 32 feedback bits. Okay. So this is a system where the analog output is trained regardless of the amount of feedback B. And this solid curve is a DNN trained specifically for every single B. Okay, you see that we do have a little bit of sum rate degradation when we generalize our system to different feedback bits, but the degradation is relatively small. It does work with wide range of feedback capacities. Okay, so let me summarize the part 2 of this talk. In this part 2 of this talk, we showed that the design of a downlink FTD Massive MIMO system with limiting feedback can be formulated as a distributed source coding problem. And to solve this distributed source coding problem, we propose a deep neural network framework. And we saw that the downlink training, the uplink feedback, and the downlink precoder can be designed together in an end-to-end fashion. We use a user-side DNN, replicated k times, as well as a base station side DNN to perform this overall task. So this joint design does 3 things at the same time, and we investigated how the proposed DNN architecture can be generalizable with various system parameters. Okay, so let me conclude this talk by saying that traditional paradigm for communication system design is always to model first, then to optimize. What machine learning allows us to do is to pursue a data-driven approach. And this approach performs hybrid. We showed the success of such an approach that performs hybrid precoding without explicit channel estimation. And for the TDD systems and for the FTD systems, we showed that such approach can perform channel estimation, feedback, precoding, again without channel estimation. And the key issues here are generalizability. Training complexity is, I haven't talked about this much, but it takes 500,000 or so training samples for this to work. And what we really need to do is to design architecture, neural network architecture that fits the channel structure, fits the overall problem structure, and that's important. So I'm really interested in how far we can push machine learning. There are really many open questions, and I'm open to any of the questions that the audience would ask. So here are 2 papers where the material from this talk is from the code for these systems on GitHub. One of them was published in GlobeCon, and the other one is to appear in the Transactions on Wireless Communications. Okay, thank you. So this ends my presentation, and I'll be happy to answer any questions.